that is a mechanism to get rapid climate change. So Carl's paper really was nothing but a schematic theory, almost a cartoon model. But it's something to think about, keep in mind, and as people get better dates for some of these sea level curves and things, it would be useful to work this out with a real numerical model and see if some of this works out. The second example I'll show you is from Walter Munk and Bruce Bills, Tides and Climate, some speculations. They were looking at the 41,000 year variation in the Earth's obliquity. Now remember, the obliquity is the Earth's tilt, the 23 degrees, but that 23 degrees isn't exactly 23 degrees. It changes from 22 to 24 about over the course of 40,000 years. So people have used that change in the obliquity as part of the Milankovitch cycle to explain changes at 40,000 years in the coming and going of ice ages. And they've blamed that on changes in solar insolation. As the Earth's tilt changes, that changes the insolation into the Arctic, which changes climate. But it's a very small change. You know, the tilt is going from 22 to 24, roughly. So Walter looked at, well, if you have an obliquity change, you also have a change in the tide. So if tidal mixing is actually occurring, as Munk and Wunsch claim, and Walter believes it does, then potentially the tides could explain this 41,000 year Milankovitch cycle. So I'll just read you Walter's last sentence, however. This speculation involves even more than the usual number of uncertainties found in climate speculation. So typical Walter Munk there. But again, that's something to think about, because there the tides are giving you something that, in theory, could explain one of these. And really, if you think about insulation, that change in the Arctic is so small, it's kind of far-fetched that could cause an ice age too. So it's not so far-fetched that the tides could be doing it. I'll give the last word to Carl Wunsch. Back in 1990 at an IUGG meeting, it was some kind of a global general session on the state of affairs toward the end of the century. Carl came up with a list of significant hard problems in physical oceanography to be solved in the next century, meaning the century we're now in. And this is Carl's 4 problems, and you could probably think of some other ones, but this is Carl Wunsch's 4 problems. Mixing with all its ramifications, including scale dependence, boundary enhancements. Air-sea transfers, where and how the tides are dissipated, detailed understanding of the interactions in the internal wave field. So if you think about what I've just discussed, you can see that we've actually hit on 3 of those 4 topics. And that, I submit to you, is why oceanographers started paying attention to tides again. So maybe some of these ideas will hold up, maybe they'll go away, but for now, there's still some life left in the old Victorian subject. So thank you very much.
Thank you, Richard. That was great. We have plenty of time for questions if anybody's. Thanks, Sarah. Yes, Al.
Why don't the continental margins behave more as a reflector for the propagation of internal tides or surface tides?
Well, it does. In fact, you can take some continental margins and do experiments with either removing them in a numerical model or putting a new one in and closing off the Hudson Strait or something like that. And it affects the tide throughout the whole Atlantic Ocean. So you do get reflection, but you also get dissipation because the currents are very strong. So if you just compute what the frictional forces is, as you have like a meter per second current going along the seafloor, that's a pretty large friction.
Any significant reflection would be all kinds of constructive interference and destructive interference?
Yeah, that's right. Yeah, that's right.
So you
And it happens particularly in the Atlantic, because the Atlantic, like I said, it's a little bit in resonance anyway, compared with the Pacific and the Indian Ocean. So you can run these numerical experiments in the Atlantic, and it's a lot more fun than in the Pacific, say. Yeah.
David? Question about the Arctic and the sea ice. As it starts to melt away and eventually have no sea ice in the Arctic Ocean, what effects will that have on the tides in that area?
Yeah, well, I can't answer that directly, but I think it should have some effects. To some extent, the way people model sea ice in a barotropic model is by simply doubling the bottom friction, because you have friction on the seafloor and you have friction now at the top. And a nice example is Hudson Bay. In Hudson Bay, it's covered over in the wintertime, but in the summertime it's open ocean. And if you look at what the tide is, summer versus winter, it's a big change. At Churchill, the amplitude of M2 is, I think it's around 1.5 meters, I'm pretty sure. But summer versus winter, the change is about 10% of that. So it's a big change in the amplitude of M2 at Churchill. So I think something similar would happen if you removed the ice from the entire Arctic. You would definitely see changes. How big that is, how much it affects the rest of the Atlantic, I don't know. But yeah, you would definitely see changes.
Where there's ice and cold, we don't like going there. Live in Florida for a reason.
Although it helps satellite altimetry, though, because you can get a lot better data when you have open water than you have. And in fact, I have some nice maps of ERS altimetry and EMVSAT altimetry, which goes a lot higher up than TOPEX does. And you can see in certain seasons the Chukchi Sea ice disappearing where we didn't have any data. We suddenly now have data. So at least for some applications, it's kind of nice to see that ice go away. We do have some data where we never did before.
For the inconsistency you show between the altimetry result about the internal tide dissipation and the tidal modeling, because we know that the ocean circulation, mesoceal eddies, as well as the ocean stratification, affect the
this thing here.
Yeah, I mean,
Yeah.
we know that can affect the internal tide conversion, propagation, and dissipation. So that means the ability of the model to represent the circulation, mesoceal eddies, and the other processes is very important to address this.
Yeah, that's right.
So I
That's
don't
right.
know whether those studies show this. I mean, before going to internal tides, did they do some validation to check whether they can represent circulation?
Right. Well, there have been papers on just that, and in fact, the slide right before that was, right there. Steve Janes was an example where he had an ocean general circulation model running in the standard way, and then he put tides in some fashion. Now the question is, he probably didn't do it right. Nobody knows how to do it right. But anyway, he did it in some fashion, and you see these changes. And that's definitely the case also when, like the Stennis group puts tidal forcing, and all of these are brand new. I think there are only, so far as I know, there are only 3 global ocean circulation models that are forced by both the usual, winds and buoyancy forcing, and also by tides. So a lot of details on how to really do that still have to be worked out, because even though these are really high resolution models, they're still not high enough to be able to model everything. They still have to parameterize things like how an internal tide dissipates.
Yeah, I'm just curious about the ability to kind of represent the larger scale features.
Yeah.
Because this is small scale or mesoscale features.
Yeah.
If you don't represent that well, okay.
Yeah. And even these models, even though they have a very good spatial resolution, that spatial resolution is good enough maybe to capture mode 1 or mode 2 internal tide. It can't capture the generation mechanism where you have high modes or beams. It can't do that. So a lot of this is still based upon parameterization.
So this one, this is Brian's, yeah?
That's right. Mhm.
So I was talking to Brian Arvick, he's the one who's been working with HICOM. And then there's another way, another twist on this too. There's another reason for putting these things into the HICOM. It's one thing I was curious about and asked Brian about years ago, is as these things are propagating away, then they're encountering changes in the stratification. For the mesoscale changes in this, which affects propagation, you expect scattering. So these waves, as they go, you would expect all this kind of scattering, but you don't see it. These things go as beams just all the way, from Hawaii to the Aleutians. So why the lack of scattering? It's like the non-Doppler effect sort of question.
Yeah.
We don't see that scattering, which always puzzled the heck out of me.
There is some that can be seen in the altimeter data, and there's a really nice example where none of these things can get across the equator in the Pacific. And the theory is that the jets along the equator there are so strong, the internal tide comes in and it just gets wiped out. So,
I always thought there should be more.
and that could also be happening in some of these boundary currents where I'm blaming it on noise in the altimeter data that I don't see any signal in the Agulhas or the western Atlantic there near the Gulf Stream. And it could be that there's no coherent internal tide there anyway. It just wipes out
You're
with
right,
the
it'll
Gulf
be
Stream.
consistent with scattering
Yeah.
as well. Other questions? Yes.
I'm really interested in the video tidal model of the different magnitudes on magnitude.
Right.
So I'm wondering, what is the underlying dynamics considered in those tidal models to represent the images?
Yeah, so that's a problem because as soon as you take away a lot of these shallow seas, shelf areas, your normal way to dissipate the tide is gone. So you're really dependent more upon this internal thing out in the deeper ocean. And whether we've been able to model that correctly, well, we haven't been able to model that correctly. But in some fashion, there's a lot more relative energy being dissipated out in the open ocean here than there is here, simply because the shells have disappeared on you. And so I wouldn't trust a lot of that because we don't know the stratification, at least I don't think we know the stratification 20,000 years ago well enough to model some of that. But the fact that the amplitudes are all large there is pretty robust. Now, this is from a paper that Gary Egbert and I wrote in 2004, but there have been a number of papers since then. Peltier's group has done one. Matthias Green in Wales has done several. Brian Arvick had one too, I think, in which he showed large tides there at the Labrador Sea. And so I think that's a pretty robust effect. You do get much larger tides in the North Atlantic 20,000 years ago.
So what about the patterns in the Antarctic region? That as robust as the North Atlantic?
You know, I haven't paid much attention to that. I mean, just by looking at this, it looks like the Weddell Sea is a little stronger right there, which would be interesting, of course, because you have all those interactions between the floating ice and the tide, and if the tide's larger, then you're doing more to that ice shelf.
So I think we're getting just a little past 4:30, so maybe we'll take one more, and if you have other questions, just come up front afterwards, okay? Brad, do you mind hitting for us, please? You beat your hand by about a third of a second.
Yes, we have plenty of time for questions.
And we've been at it for 10 minutes.
Yeah, give me a break.
Officially, the seminar is supposed to be at 4:30, so to be polite to everyone.
Just extending to what was said about the circulation, there is one aspect which wasn't even discussed. Because the change in stratification may change the dynamics and distribution between the energy cascade, between direct and inverse cascade.
Yeah.
You have inverse cascade in all these models. Brian Arvick also showed it in his simulations. And distribution energy between these two cascades will do a lot of damage to dissipation and composition.
Yeah. So I would say, I mean, one of my bottom lines is that there's an awful lot of work to be done yet on that chain.
Okay, well, thank you all.
Yes, thank you. Well done. Very nice job.